Okay, in the beginning, let us review the Maxwell's equation. Before that, let us define the EM field. E here denotes the electric field vector, and here is the corresponding unit. H here is the magnetic field vector. D represents the electric displacement vector. We also call it as the electric flux density field. B here is the magnetic induction vector. Before we go in the following part, I have to remind all of you that if you want to express the vector field, in writing, if you want to express the vector field, please use a bar or you can use an arrow to let us know that what you mean is the vector field. But for scalar field, you can just write like this. So if you want to mention vector fields, please remember to use a bar or an arrow to let me know that this is a vector field. Besides, we also have the source to induce the EM field, which are rho is the electric charge density, and the J is the electric current density. All the quantity above, they are functions of x, y, z, and t. So, since we have defined all these quantities, let us write down the Maxwell equations in differential forms. First, we write down the two curl equation. We know that curl E equals to minus partial B over partial T, and the curl H equals to J plus partial D over partial T. And we also have two divergence equations, which tell us that divergence D is equal to rho, and divergence B will be 0. These four equations are Maxwell's equations in differential forms. As we are in the department of photonics, these four Maxwell's equations is very important for us. So you have to keep all these equations in mind. To understand the physical meanings of the Maxwell's equation, we have to transform the differential forms into the integral forms by using Stokes theorem and the divergence theorem. For the Stokes theorem, consider an open surface S. The open surface here means that you have the contour C. So S is an open surface. C is the corresponding contour. Over this open surface, you can cut it into many small pieces. Each piece has its surface dA and the direction n hat. As a result, this surface is a vector field because it has direction. Also, along the contour C, you can find out a small section and has the direction, so this is a vector dl. The Stokes theory tells us that if you perform surface integral of A over the open surface S. This surface integral will equals to the line integral of A along the contour C, which C is the contour of the open surface. So you can easily transform the curl equation into the integral form here. And following the similar concept, for the divergence theorem, consider a volume V and also you can cut the volume into many small cubits. Each cubit has the volume dV. And this volume is also enclosed by a surface. And the surface of the volume can also be cut into many small surface dA. And each surface has a normal vector n. So S here is the surface of the volume. After we define here, the divergence theorem tells us that if you perform the volume integral of divergence A, for vector field A, if you perform the volume integral like this integral will equal to A dot dA over the surface S. The S here is the surface of the volume. So this result can also help us to transform the divergence equations into the integral form like this. Okay, let's see how to use the above two theorems to transform the differential forms into the integral forms. For the curl equation, curl E is minus partial B over partial T. So let us perform the surface integral of this equation over an open surface. For the left-hand side here, the surface integral will become curl E dot dA hat over an open surface S. And the Stokes theory tells us that this will become E dot dl over along a closed contour C. C here is the contour of the open surface. This means that if you perform curl E over an open surface, this will equal to the closed line closed line integral of E along the C, which is the contour of the open surface. And for the right hand side here, we also do the surface integral. It will become minus d over dt and b dot dA over the same open surface S. And for this one, we know that this will become the magnetic flux. So it will become minus d phi over dt. Okay, and the final result is the well-known equation, which we call it as Faraday's rule. Following the similar way, we can consider the second curve equation, curve H. Also, we perform the surface integral over an open surface here, and by the Stokes theory, we know that this will become H dot dl along the closed contour C. And for the right hand side, you will have d over dt for d dot dA plus the surface integral of J, and we know that J is the current density, so the surface integral of J will become the current I. Okay, since that, consider this side here. These two shall have the same physical meaning. Since this one is current, we can also say that this one shall also be a current too. So what kind of current it will be? We call it as ID. This is so-called displacement current. And we know that all this component is displacement current. And the displacement current comes from the the integral of the current density. As a result, we can define that the corresponding current density of the displacement current will be partial d over partial t. So partial d over partial t here will define as displacement current density. So if you perform the surface integral of partial d over partial t, you will obtain displacement current. And this equation is so-called Ampere's equations. So Ampere's law. And then now, let's go to the divergence equation. If you, for divergence D, okay, for divergence D, if you perform the volume integral of divergence D over in a volume V, by divergence theory, you know that this will equal to the closed surface integral of D over a surface S. And the surface S here is the surface of the volume. And on the right hand side, it will be low dV, the volume integral of low. And this will be the total charge in the volume. And we call this equation as Gauss rho for E. Okay? And finally, we go to the divergence B. If you perform divergence B in a volume, perform the volume integral of divergence B, by the divergence theory, it will equal to the surface integral of B over a surface S, which encloses the volume V. And I believe that all of you should know that this closed surface integral will be 0 here. And we know that this is the Gauss law for B. Okay? And we all know that this tells us a very interesting physical meanings. This means that the total outward flux of B will be 0, which I can plot here. Consider a volume here. If you want to know the total outward flux, we have B inside, we have B outside, and we know that the total outward flux equals to 0, means that the total inside here will be the same amount of the total B outside the volume. This means that if you have the magnetic field line outside the volume, and the same magnetic line will go back here into the volume. And this means that the magnetic line is a closed loop. Okay? Why the magnetic line is a closed loop? Because that each magnetic line will start from the N pole and will be ended at S pole. Since the magnetic line is a closed loop, this means that the N port and the S port, they should be on the same point. So we can have the following conclusion that no isolated magnetic charge. You cannot separate N from S. These two always on the same point, and this makes the magnetic line start from one point and end at the same point. As a result, the total magnetic field outside the volume will equals to the total magnetic field into the volume. And the above 4 equation is so-called Maxwell equations in integral forms.